We're ready to start. So let me check. Can you hear me? Can you see the presentation? Good. Well, good morning, everyone. Thank you. Many thanks for joining this Sunday. Apologies for the confusion we have in LinkedIn. But many thanks for joining these sessions, and I hope you all, you and your family, you're all doing good during this crazy time. But that's the way. It is what it is. So I hope you are all doing fine. I really appreciate your interest in joining to this session this morning. So this is going to be a very, I would say, very basic in terms of the theory behind this. It's just more like a practical application regarding production system analysis. So just before starting, I just want to make sure that we follow some rules here to guarantee that the session is going to be effective and don't use too much bandwidth. So feel free to participate at any time, but I mean, I would appreciate if you can turn off your camera and mute you all. In case you want to participate, you can do it in many ways. I mean, you can send a message, or you can also switch your camera on and make any question at any time. But for the time being, just keep your camera off and mute your mic, please. Okay. Without further ado, let's start off. The topic of this morning session is morning over here. So we're going to be talking about production system analysis. I just have 2 or 3 slides. I promise that it's not going to be too extensive. So my plan is to go very, very briefly on the fundamentals. We have more people coming in. Fundamentals of production system analysis. I'm going to show you the psapy library, and we will go through some exercise that we prepared for you this morning. Okay. I bet that all of you are very familiar with these figures, so it's just to frame you on what we are going to be talking about. Is a production system is very broad concept, but for this morning topic, we're going to be concentrating in what I call near wellbore system. No? So it's coming from the boundary, or it's coming from the drainage area all the way up to the separator. And in this case, we are looking at only one piece of the picture, which is one single well. But keep in mind the broad picture, which is, I mean, the full field and everything integrated. So it's just this is just one piece of the cake. But in general, what the intention is, I mean, we want to optimize or maximize the energy available. So starting off from reservoir all the way up to the separator, given my boundary conditions. So normally we have a minimum separator pressure and we have maximum reservoir pressure. So we want to find the balance points between these two, taking into considerations all the possible restrictions that we have in the system. So we start from porous to flow through porous media. So we have here some delta P, normally associated through the flow through the reservoirs. Then we have some additional delta P going from the reservoir or into the wellbore. Then we have another pressure drops associated with the restrictions and all the type of completion we have, and associated with the type of fluids we have. And we go all the way up in the same way to the separator. So starting from the reservoir, so which is the first part of this session. So the simplest way we have here is the IPR. I'm sorry, it's very slow here. Okay, there you go. So when we are dealing with monophasic reservoirs, we know that we have a linear relationship between the rate and the pressures. And normally the inverse of the slope is given by the productivity index of J. So keep in mind, we're dealing with, in this case, when my flowing pressure is by any time above the saturation pressure. So if we are in that condition, it's going to be pretty easy to estimate what the productivity index, or J, will be. So if we have a well test in which we can measure the rates and stabilize pressures and flowing and static, so we can estimate what the productivity index would be. Or if we have additional parameters like effective permeability, thickness, PVT properties, we can also estimate or guesstimate, because we don't really know what all these parameters are really all about, what the real productivity index is. So in this way, we have from one way the Darcy equation involved, and from the other way we have production data. So depending on the data we have available, we can build very quickly this IPR model. So it's not too complex, and of course we are dealing here with a pseudo steady state approach. So we have nothing transient in this calculation. So when my reservoir pressures or my flowing pressure goes below the saturation pressures, the linear relationship is no longer there. So we need to start taking this into consideration. So one of the mostly used approaches is the Vogel. Vogel, he did a very nice estimation. So he made different calculations with a different depletion rates and also a different type of deliverabilities, like we have here in this figure, the A and B. And when we normalize this in terms of pressures, and when we normalize this in terms of rates, you find out that everything aligns very well in a I would say pretty unique shape. And of course, this is using, or he estimated only using for gas drive reservoirs. And he come out with, I would say, let's say a regression, which is pretty easy to estimate. So if we have only flowing data or production data, we may have a way to estimate what the productivity index is, or we have a way to also to describe this IPR when we are below the saturation pressure. What we also assume that right above the saturation pressure, we have or saturation or reservoir pressure, we have a linear conditions. So we can find a way to integrate Darcy equation, which is only valid for saturated or subsaturated reservoirs, integrate with the Vogel model, and have a way to also expand these equations in terms of reservoir properties. And in reality, what we have is a situation which is a combination of both. So we may be in a situation where my reservoir pressure is above saturation pressures, and if we have a linear relationship, at a certain point we reach the saturation pressures, and then we go into the nonlinear relationship. In this case, we are using Vogel, but we know there are many other equations over there. But what we are doing here, if we take this point like the bubble rate or bubble point rate and the bubble point pressure, we can equalize the two equations and obtain, like I would say, a combined way to estimate what the IPR will be. No? So this is the reason I'm showing this is because we have a library. And in these libraries, we're using normally for most of them, the combined equation. to estimate what the IPR will be. Then I don't want to go into this because it would take a lot of time, but we have also a part of the library is focused on the multi-phase flowing pipes. You are aware, I mean, the way to estimate the flowing pressures is very challenged. Normally, we are using a lot of correlations, empirical correlations that were developed in the 70s and the 60s. In fact, I wonder what we would do today with all these technologies available, and when we have machine learning and deep learning, they may come out with something probably different. But the beauty of that they're in somehow they are attacking all the physics that is present in this. What is the challenge, of course, here is to estimate the friction components when we are in a multi-phase flow with a liquid that is normally the non-Newtonian liquid, and we have a lot of physics going on this. Okay. That's all that I have for you, and this part is just to frame you on what we are going to be talking about. For today, it's going to be very basic. It's going to be one of the first sessions is just a way to build the IPR. And also we're going to have a way to build the pressure traverse and do some exercises using some in many cases, but we have this library, which is fluids props library, is combining both oil and gas correlations and also water, I guess. It's just to give you an idea of what is behind that. Nothing special, but very handy. So we also have gas prop. It's just like a breakdown of the fluid prop and just extracting the gas property in case you want to use it, especially only for gas. The same for oil props and the same for water props. So this, but everything is combined and integrated into the fluid props library. Okay, more exciting than that, we have into the Vogel. We shouldn't be using that name, but Vogel is in reality the IPR. And in that module, what we have the three components that we just recently discussed in the slides. So we have one function, which is Darcy IPR, very quick and linear, which is nothing else like the linear. This one right here. And this, of course, this is assuming that we have reservoir properties. Then this is what we call Darcy model. Okay. Jump into The other one, we have the Vocal Ipr. This function is a very simple function. This is used only in the case when we only have measured data like pressures and rates. And then we have Vogel-Darcy IPR, which is the equation that combines both. And this is assuming that we know reservoir pressures and reservoir properties like Ka, viscosity, RE, etc. All right, and we also have another very nice library, which is for the multi-phase flow. We have two. We have Bex and Brill. We know very well about this correlation. And we also have Hagedorn and Brown. We have tested more Bex and Brill, Hagedorn and Brown. I've made some tests. It's working fine, but I can't guarantee it's bulletproof right now. Okay. So within the Bex and Brill, we have different functions. And the beauty of this is that, of course, to calculate these, we need to have PVT properties, and we need to have different variables that is using the libraries inside the same PSA. So we have this function we call pgrad, which is only calculating the pressure gradient for a given piece of length of pipe, okay, given diameter and given angle. So if we want to do a pressure gradient, for example, we have to integrate this into different pieces depending on the variability of your diameter, or if you have any other variable also changing through the pipe. Okay, as we remember, Bex and Brill is valid for any angle. Although there are discussions about, the applicability on vertical wells, but I have seen cases where it also works well. The main point of discussions on Bex and Brill is that Bex and Brill was, when it was developed, all the tests were made using water data instead of oil, and was also made using a very slim pipe of only 1.5 inches of diameter. So it may have some people that they don't like it, but this is one of the standards. Hagedorn and Brown is also being used very extensive. No? So within the same library, we have another sub-functions to estimate the flow regime, which is the core of these correlations. Friction factor in this case for this for this library, we're using the Chen equations to estimate the frictions, but we know this is not a unique solution. There are many correlations available also for friction calculations. We also have another function which is very similar to the pressure gradient one. I don't remember exactly what the difference is, but I think we use the first one normally. And we have also another one which is calculating the flowing pressure given the rates. Okay, and this is just a subroutine, just calling the pgrad function. So if you want to estimate what the flowing pressure is, just call this function. Or if you want to do it by yourself, you can also integrate the p gradient into pieces and do your calculation by yourself. Keep in mind that if you assume that the length of each session is too high, we may lead to some inconsistencies. We need to find a sweet spot on the pipe or piece of pipe or that we are going to integrate on this. Okay. So far, so good. Any question to this point? I can move ahead. Okay. So now let's jump into Python itself. So as I mentioned, for this library, we have to install the psapy. So the way to install is going to be very easily. So we go to we can open a terminal and let's use there you go. We can use pip install psapy, and that's it. I should have an install. Yeah. But if you are doing in your home, that's what you need to do. Make sure that you also have installed matplotlib, Seaborn for the plot, this both for the plot. And I want also to include SciPy, especially interpolation. I like this function to do interpolations as well. So let's click this and run this. Perfect. So I have here preloaded some pressure data, some data. It's nothing, it's not real data, it's just invented by myself, just to test the equations. So first thing that we need to, just to check, we can use the saturation pressure. Let's see if my function is working fine. So I just need to call fluid props, because that's the alias I use for fluid props. So we go fluid props, and then we can call a function bbob, which is the saturation pressure, bubble point pressure. And the inputs, if you don't know what the inputs are, you can, if you do, I think it's Ctrl+Shift Enter. Yes. If we do Shift-Tab Enter, we have a short description about the inputs. We have temperature, separator pressure, temperature, separator pressure, gas gravity, oil gravity, and GOR. We also have a very short description about the information about the correlations and where it's located. So we need the temperature, which is named temp, 150 in this case, 75, let's assume separators or standard conditions. We have the gas gravity, API, and the GOR. Yeah. Oops. Temp. Okay, I need to run this. We want to print this. OP set. There we go. This is using standard correlation, and is calculating that my saturation pressure for that given condition is 2370 psi. Okay. So it's just a quick and dirty way to check that my library is working fine. So we have a new line. And now let's use the Darcy IPR. So another way is that if we use for IPR, remember this is my alias right here. I'm using the Darcy IPR underscore underscore doc underscore underscore. We can have only the documentation part of the function. It's just a quick tip. Okay. And let's check something here. Shift-Tab Enter. tab. So we now have the arguments I need for that is permeability, thickness, viscosity, external wellbore radius, the skin, static pressure, oil formation volume factor, and endpoints. And in this case, since we are building a curve, this is referring to the number of points I want for this curve to be built. Okay. So let me define the number of points. 10. And let me pull my curve. And that's it. So I have my IPR. Let's check what is given my results. There you go. But it's also important to know the type of output we are getting out of these equations or these functions. So the output we have is two pair of lists. It's not an array, it's just two lists when we have rates and pressures. And we can also check on GitHub. Let's go here, check this tab. If I go to Vocal, for example, that's what we're doing right now. We are using Darcy IPR, and as you can see, it's returning a pair of lists of rates and pressure. So this is the type of output we are getting out of here. Okay. So let's do a quick plot out of this. Let me add a new line. Sorry. Oops. I don't know what happened. Let me. There we go. So in this case, I use the Seaborn library, which is another visualization library. It sits on top of the matplotlib, and it does have more flexibilities and functionalities for a nicer display. But you can use any library for visualization that you are more familiar with. So in this case, I'm just plotting the X is going to be the first list. We know this is the rates. And for the Y axis is going to be pressures and linear relationship. So if I change the number of points to 2, of course, we are going to get the same results, no? Because we have a linear relationship. That's fine. So let's try now and test the other equation, which is Vogel. And I just copy here the inputs for the Vogel. And we have 500 points. That's ridiculous. It's too much. Okay. So let me use 10. So the same way. So we have here the output is a pair of rates and pressures. And let's do another plot right here. Should be working fine. Okay. Now we have Vogel. Very nicely. It's not a big complication. That's fine. It's not rocket science. So if we move further now into the combined IPR, so we're going to be using now the other function, Let me continue. So for the IPR combine, in this case, we need to call the Vogel-Darcy IPR function and just put the inputs and it should be fine, right? And the same way we can do the plot. Let me copy right here just to make it more simple. Another plot. I need an IPR right here. Okay, and we have just one plot with only 10 points. And I want you to discuss, I want to discuss something with you is regarding the type of outputs we have here. So, you know, we have a discrete type of output. So we have only a number of points that we decide. So that means that this is not a continuous function. No? So we don't have a value for every single point. So there are many ways to deal with that. So you can do a regressions if you want and get a pressure for every single rate. We can do also something more simpler like interpolations. And this is why I want to use the interpolation function, for example. Let's define that we have for my x variable is that we know the rates. This is the output of the let's see this output IPR combine, and let's just define two functions. It's just to show you two different type of interpolations. So we have function one. You can go to the manuals and check on the documentations all the input for this library. It's very simple. So by default, it's going to be linear if you don't define any kind of or type of interpolations. So we have x and y's and two different functions. Then let's create a set of it's just a vector, an array with a minimum value of 0.1, the maximum, let's say, should be around 40. This is 40,000? Yeah, let's say 40,000. And I want, I don't know, 100 points. Okay. And also I can do a plot now integrating the tree. Okay. So I'm using a plot that I have for one is x and y, and this is the type of marker. For the other one is x new, which is just the output of this array. And we have the f new, which is going to be the output of the linear interpolations. And with this type of marker. And then we have for the new x, it's the same type x, the output of my array. And the f2 new is the output using cubic type of interpolation, which is, you also have a spline and another different methods within that library. So let's see. MP, okay. I need to import. Sometimes it's laggy here. So I have this error because I haven't imported yet the NumPy library. So let me do it right here. For NumPy as MP. There you go. So if we use semicolon right here, it won't create this object, and you save some space right here. That's fine. Let's expand this. I don't know if this is 50,000. So it's throwing an error because I'm going beyond the limit of my input. So let's see, 42. There you go. So what I want you to show you is that we have a way to optimize the output. And this is going to be very important, especially in the future, for future sessions, when you don't need to be calling the IPR library and doing all the calculations behind, especially if you are dealing with a very intensive or or calculation with a high frequency. High frequencies might be at different timings, or we have multiple wells, or both. So if we just save the output in a way of a single table, we will have a way to obtain any value just by using interpolations. And depending on the spread of the points, probably linear interpolation could be valid. But I have found that qubit is working also very well on most of the situation for the IPR. So that's all that I have for the IPR. I just wanted to know if you have any kind of question in this part. Okay, move ahead. Okay. Now let's move to the other part, which is the pressure traverse. Okay. Okay. Low right here. Okay. On the pressure traverse, we are going to be using the other part of the library. Normally using the Bex and Brill as a multi-phase follow correlation. Okay. I already have preloaded a set of input data. So we're just dealing with an oil well. Excuse me. The way we presented the equation, or we wrote the equations in the behind, is using a water rate instead of water cut. So you just need to be doing the conversion as needed. So we have the GOR, oil gas gravity, water gravity, where this is a diameter of 2.441. Is a vertical well, and we have the tubing pressure and the temperature and the flowing temperature. I just created here a very simple function just to estimate or to do a linear pressure temperature gradient. So if we have the gradient at the wellhead and the gradient at the bottom and the depth, so it's just the output of this equation will be the gradient. So delta T over delta depth. This is going to be convenient. It's just for okay. Now to do the pressure traverse, what we built here is another function calling the P grad, or the gradient function, in the library. So, and what we are doing here is just we have the input is oil rates, and I want to show you why. And we're going to be going into the different depths, and to each single depth, we're going to be calculating the pressure gradient, and we are going to be adding this delta P to each piece of the pie, and then we're going to plot both. So before that, let's test this. Let's define some depth right here. using NumPy. I'm not so sure if I run this. Let me run this. There you go. So now let's check if we have some depths. I'm just getting. Yes, one array, and we are having a step of 100 feet for each single piece of pipe, and going all the way down to 5,000, which is the final depth. No, I just did it. So we can do even further optimization on this to see if my steps are okay, or we need to do more refining on this. Then we can create also, let me do it right here, an array of temperature. Okay. And here. So what I have here is a temperature, the output of my temperature gradient function. So for a single piece depth, we have what the corresponding temperature is going to be. And this is very inconvenient because we are going to be passing this through the functions in a form of an array, and we're going to have everything already calculated. Okay. So let's check here. We have a pressure traverse. This is just a defined function. My input is the oil rate. And we created here two lists, one for pressures and the other one for gradients. So we are going to be iterating for every single depth, so from the surface all the way down to 5,000. And for every single piece, we're going to be adding the gradient. So that's what we are doing here. So we calculated what the delta in depth is going to be for every single increment. What we know is already 100. So the difference between one step and the other. We have the pressures, okay, which is going to be the pressure of the previous step plus the delta P. And we're going to be adding this into the pressure list. Okay. So if we run this, we have, okay, that's important as well. The output of this function is a pair of pressures and gradients. So if I call this, and we have pressures. This is the last pressure. I also print everything. So we have my array, which is starting from the wellhead pressure all the way down to the bottom. And this is assuming that my flowing bottom hole pressure, or at this depth, is 2313. Or if we want to extract only the last one, that's what we're doing right here. If you need a DPDC, we just print it, DPDC. Let's print the whole array. Yeah, we have the variation of my gradient from the bottom to top, or top to bottom, depending. So the beauty of that is that with this information, we can use this information to create a plot. Let me clean this up a little bit. For example, if we have, I'm plotting here the pressures, all the pressures versus depth, okay? And what we have here, the pressure gradient, which is pretty handy. And do you know, you may still asking, why do you created this function as a function of oil? It's just an easy way to manipulate, because if my input is not a single rate, but if we have a list of rates, let's assume, right, I don't know, I have 5 values of oil rate. So I can call my function for every value and create my plot. And we have now the different pressure traverse for different rates conditions. Of course, you can do the same, you can do magic with that, in the sense, I mean, using now the power of Python, because you can create, instead of an array, you can create a distribution, okay, and obtain it's going to be a matrix, a huge matrix of a possible outputs. Or instead of calling the full pressure gradient, you may have a distribution of the bottom hole pressure at given depth, just by calling the the last value of the pressure gradient. Okay. Nice, no? So keep in mind something. Now, when all this theory was created, so we are talking about the 1973. So probably Alejandro was born already at that time, and and the technology available at the time was very, very limited. So it was created mostly with the intention of, okay, we may have a gauge at the surface, but I need to know what my flowing pressure is at bottom hole. And it was the main driver to develop all these correlations. Nowadays, it's very common, most of the new fields or relatively new fields, to have a downhole pressure data. And this is what we are going to be doing for the next session. So we're going to be integrated real measured data and see a way that we can use to calibrate my correlations and try to force the correlation, if possible, into the measured data. It seems to be very simple here, but we have a lot of variables that we don't manage very well. In terms of, we are assuming that this is my diameter, but in reality, and we know that we have this is a dynamic condition. So the condition of my well can be changing through time due to erosions or different type of events that might be occurring on the well. So every single change on the impulse will have a huge impact on the frictions calculation. So sometimes we adjust the friction coefficients, sometimes we adjust the gravitational coefficients, sometimes we do both, but we want to do it within a limit, no? So that's a part of what we're going to be doing on next. I just want to set the basis on this. So any questions so far? Mm. Okay. I don't know. I can send you an email, a dedicated email separated on that if it's going, if you need more detail on this. No? But, okay. So now what we're going to do next is, what if we use, instead of having the pressure gradient or the pressure traverse, what if we use the calculated flowing bottom hole pressure to estimate or to build now the vertical lift performance curve? that is something that we use a lot. So it's just using the same equation or the same procedure, but in this case, we are going to be only extracting the last point. And we are going to be changing the rates. Okay, so I need this point, this point, this point, this point. And we're going to be building the vertical lift performance. So this is in the new Jupyter notebook. Let me remind right here. So it's the same input. Okay. There's nothing new here. Right. Now, as I mentioned, what I need to do is something very similar to what we did. Okay. And slide it here. And create another function we call VLP, which is something like this. Okay, so in this case, we created a new function called VLP, and the input is now rates. Because remember, to create the VLP, we need a pair of rates and pressure. And I open an array of buttonhole pressures, and we iterated in different rates. Okay. And for each different rate, we are just extracting the last value. And the output will be only a list of buttonhole pressures. Okay. So let's create an array of rates. In this case, I have between 100 and 5,000, I want 50 points. Okay. And for each single one, let's calculate what the buttonhole pressure will be. Okay. Oops. Drivers. Yeah. I haven't run this yet. Oh, this is not library. This is psapy. Psapy. There you go. So let's check my output. My output is going to be, it's just a single vector with a bunch of flowing buttonhole pressure for rates. Excellent. So I know it's working. So now what I need to do is very simple. It's just plotting. Okay, for the rates vectors and the buttonhole pressures, and put some labels. Nice. So what we've built here in this hour is just an easy, a quick and easy way to create the vertical lift performance. Okay, this is using Bex and Brill. Keep in mind that this correlation is not calibrated by any means or to real data. So we just assume that that's my data I have, and that's the type of output I should be expecting. And of course, moving forward for the next sessions, what we are going to be doing is integrating this with the IPR to obtain my operating pressure, operating rates. And we also we can be doing something interesting to estimate what the rate will be. If you have some time, I want to show you something really nice. Which is this. So what we have is rates and pressures, okay? But what if I know what the buttonhole pressure is, which is very common now in the reality, no? I know what the buttonhole pressure is. I know sometimes what the tubing head pressure is as well. I don't know the rates, or the rate might be estimated at different frequencies. So what I'm trying to say, normally what we do to estimate the rates, unless we are in a reality that is when we have a meter, we normally send the well to a separator and test the well for a couple of hours or day, depending on the situation, and estimate the stabilized rate. And then we try to extrapolate what the pressure are and to estimate what the conditions are of the well. So, but what if we have an output, I don't know, every seconds or every 5 seconds or every 10 minutes at different frequencies that we estimate the rate? So we could use one way. This is not a single way. That, in fact, it's not the most accurate, but this could work. What if we use Beck's and Brill or any other correlation to estimate what is the rate that matches my measured data? So in that way, what we are doing, we're having a virtual meter, for example. So let's do this. I have this data that is measured, or assumed to be measured. Okay? So I don't know at this point what the rate is. I estimate that the water cut is, this percentage is 33%. And there is an easy way to normally to estimate or to measure the water cut. The GOR shouldn't be changing too often, so what we have. And then we have the measured data, buttonhole pressure, and that's it. So with that, I can use this library, which is the optimizer, the solver for SciPy. Let me import it. Okay. And now let's define an objective function. So what my function is to minimize the difference between the calculated pressures and the measured pressures, given some input data. In this case, it's going to be all this data plus some estimated or initial guess rates. No? So the function could be defined something like this. So we have the objective function, and the input is my guess data. And now we have a sort of optional arguments that we can pass through. In this case, we call data. So we have a buttonhole pressure observed is the first value of my data argument. We have water rate because I mentioned that the input on the correlation is in terms of rate, not in terms of water cut. I call my the function we just created, and I extract my buttonhole pressure, the last value, and then I return the difference. Okay. So the output of this equation is, or this function is going to be only the difference between the observed data and the calculated one. So we can call this way. Sorry. Data is buttonhole pressure. Check here. Okay. 2 were given. QGuess data. Go ahead. So pressure traverse takes one argument, but two were given. Let me check here. Oh, yes, it's because I recreated the same function. I put it right here. Hold on. Okay. So let me call the function right here. So it's exactly the same function that I used to write it with oil rate. I just added water rate as well. That's it. Nice. So what is this giving to me is an answer in terms of rates, no? So what is doing is 3315, the calculated rate. And if we look at the input is 100. So what do you think is going on here? So we input exactly the same input data, but only change the guess or the initial value, the seed. So when we look at this, the shape of the curve, we know that for a given pressure, we may have multiple solutions. So in this case, what is throwing me, this is what I say, that this might not be the most accurate, but it is working. So it's throwing me the solution to the right side because we started with a pretty high value. I guess that if we use, I don't know, 10, I haven't tested yet. There we go. You see, now the estimated rate is pretty much 100, which is exactly the same rate that we use for the input. So this is a pretty nice application that we use a vertical lift performance or just a VLP correlations, in this case, Bex and Brill, and we use to estimate rates. But I also give a warning, okay? What you get as an output might not be correct if you don't know what you're doing. Okay, so this is pretty much what I prepared for you this morning. If you want to have more discussion, just feel free. The plan is to move forward to another session next week or the week after. Now doing using the same libraries, but now we're going to be constructing on top of that the nodal analysis. And we're going to be doing more rate estimations. And at the end, we want to do something more challenged or more realistic using more field data, okay? So any questions, feedback, comments is very welcome. Mm-hmm. Okay. So keep in mind what we are using, and since IPR and the VLP, this is purely pseudo steady state, no? Okay, we are not taking into consideration for the time being any transient effect. So if we have an operating data that is recently to a well event, like an opening of the well or a recent well choke, depending on the well conditions, we may have unstabilized conditions. So in that case, I would not advise to use this because we are still on the transient, trying to get stable conditions. So in other words, we should make sure that my pressures and my temperature, they look stable before going and doing calculations that is using steady state or pseudo steady state type of approach.